Thanks. Yeah, before I start, thanks again for the invitation and to the organizers for having this sort of second in-person version of this workshop. 2020, I think my title was something like on Fusion 2 categories. And today I'm essentially talking about something which you could think of as modular Fusion n categories. So we changed 2 to n and we added an adjective. So that's some progress in the last 2 years. So let's get started. So what I'm going to talk about, most of this is not yet published and not yet on the archive. Most of this is joint work in progress with Theo Johnson-Freid. There are some sort of first indications where you can see some of this stuff already in action, but the main story is sort of coming up. And so I should say, since this is all work in progress, please take everything I'm going to say here with a grain of salt, or with a heap of salt if you want. And I'll also try to be I will be fairly informal throughout the talk, and for sort of technical questions or details, it would probably be better to sort of discuss them at the end, and I really want to get sort of ideas across. So intuitive questions are very welcome, but please don't get too technical. Okay, so here we go. Let me sort of summarize the story on one slide. If I have a TQFT, particularly I'm going to look at a semisimple anomalous TQFT, you will see what these adjectives mean. But a priori, if you have some TQFT, you can look at operators of dimension k. So for example, operators of dimension 1 are Wilson lines, but you could have higher dimensional operators. I should also warn you, I'm sometimes going to call these guys operators, and sometimes I'm going to call them defects. When I say operators or defects, I mean exactly the same thing. Sometimes it feels more natural to call them operators, and sometimes it feels more natural to call them defects. And unfortunately, after I finished these slides, I noticed that I wasn't consistent in my choices. So I have this pairing. I can take an operator of dimension k, and I can take an operator of dimension n minus k, and I can sort of pair them together using one of these Hopf links, sort of these higher dimensional Hopf links. I can cross them in... No, I mean sort of Hopf, you can have a Hopf link in arbitrary dimensions. So you can have a Hopf, sort of the normal Hopf vibration comes from a Hopf link in sort of a line and a line, and they live in 3-dimensional space. So that's a Hopf link. You would usually, two circles linked. That's usually what you would call a Hopf link, which is related to the Hopf vibration. But you can have Hopf links in arbitrary dimensions, but you need to make sure that the surfaces you're linking have complementary dimensions. So if you have a sphere of dimension k and a sphere of dimension n minus k, you can link them in an interesting way in n+1 dimensional space. That's the idea. So now if I have a TFT, what this means is if I have an operator of dimension k and operator of dimension n minus k, I get this operator of dimension 1, basically. It's a point operator in n+1 dimensional space. And so if I also assume that my TFT doesn't have interesting point operators, if there are no local operators in this TFT, then I can identify the space of such point operators just with the complex numbers, if I'm over the complex numbers, and so I get a number out. And this defines a sort of pairing. And in fact, actually, so in Rn+1, so if my TFT itself is n+1 dimensional, so if you assign numbers, sort of partition functions to n+1 manifolds, this will be a point in an n+1 manifold. So it's really a point operator. It's a thing you can insert into a top dimensional manifold. So it's really a world point. It's not a world line, it's a point operator. What you get out after you do this linking. So you really have sort of turned this, right, this is a point, you can sort of contract it together and see just a point. Which you can sort of locally insert into some Rn+1. And if you don't have point operators, which you usually don't have in a lot of TQFTs that people care about, you just get a number out. And in fact, this is a pairing. This pairing actually descends to a pairing, the descents to a quotient of these spaces, namely, if I'm looking at operators, actually, the pairing will be the same if two of these operators themselves are related by a defect, have a defect or another lower dimensional operator between them. So if I can pass from one operator to another, then actually the pairing of sort of this one operator and this other operator with something else will be the same. So you get somehow this pairing on this quotient. So that's the first non-trivial statement, is that this pairing descends in this way. And then actually it turns out that if you are in a semisimple anomalous TQFT, this pairing will be non-degenerate. So it's really a perfect pairing. You can sort of learn something about operators of dimension k if you understand everything about operators of dimension n minus k and vice versa. And in fact, there is a stronger result, which is that basically a version of a converse is also true. Namely, if I'm not in an anomalous TQFT, but in a so-called relative TQFT, or if you want in an open-closed TQFT, then actually, if this pairing is non-degenerate, then the TQFT is itself an anomalous TQFT. So those of you who are sort of familiar with these terminologies will know what I mean with this. Everyone else, I'll get to this in a second. So there's really an if and only if characterization of what it means for this pairing to be non-degenerate. Okay. So let's get going, and let's start with sort of a one categorical warm-up. So everything that happens sort of in this chapter of this talk is really well known and well studied, and I'm just going to recapitulate some things, and everyone who has been to Christoph's talk yesterday will also understand everything that I'm going to say in this first section, hopefully, so this should all sound fairly familiar to you. First thing that we've seen yesterday is that if I'm in a monoidal 1 category and I have some object X in this monoidal 1 category, I can define what it means for this object to have a right dual. Namely, there exists another object X dual and morphisms called the evaluation and co-evaluation that fulfill these equations. Right, when I draw these pictures, this is the graphical calculus that Christoph explained yesterday. My tensor direction is sort of to the right and composition of morphism goes up. A monoidal category is something which inherently behaves two-dimensional. So this, for example, is a morphism from X tensor X dual to the tensor unit. Okay. But now I'm not just in a monoidal category, I'm in a rigid monoidal category. Again, callback to Christoph's talk. All objects now have left and right duals, so I have evaluations going like this, but I also have evaluations turning to the left. But a priori, the left dual and the right dual, they don't need to be isomorphic. They don't need to be the same object. So somehow these pictures suggest that we could draw something like this. But the point is we can't. And this was, of course, also the topic of Christoph's talk, really. So you already notice already that you can't form these circles without sort of doing something more careful. So the notation is in some sense unfortunate, because here it looks like I can just sort of plug this one together with this one and get a closed circle. But those are different objects, and you have to identify them somehow. If you don't identify them, you can't form a circle. And so you could ask, okay, if I don't use something like a pivotal structure, which allows me to identify these, well, what is this graphical calculus then? What is the graphical calculus of a rigid monoidal category? And the idea essentially is that you have to record something like a winding number. You have to record how often your string has been turned around. So being the right dual versus being something like a double dual or being the left dual is a sort of winding number that your string sort of carries as an additional piece of data with it. So here you can't close it up because this has, say, winding number 0, and this is winding number sort of +1 in the other one. And the way to do this formally, this comes essentially out of the so-called Hopf hypothesis in this sort of one-dimensional setting, or in this two-dimensional setting. It's essentially the Tangle Hypothesis. And this is saying the following. So this is basically, if you want, a description of how the graphical calculus of a monoidal 1 category works. So if I have a rigid monoidal 1 category and I have some object in this rigid monoidal 1 category, I'd like to draw sort of string diagrams and evaluate these string diagrams on this object and say this is a well-defined thing that I can do. But this only works if I equip this one manifold that I'm drawing, this one-dimensional string diagram, with additional geometric data, with additional framing data. And the framing data is precisely the following. First, you need a tangential framing. So you need a trivialization of the tangent bundle of this one manifold. Since it's a one manifold, this is just the same data as an orientation. So this I've already drawn, right? We've sort of drawn these orientations here. Fine. So that's the first piece of data. The second piece of data is I also need a normal framing. I need to trivialize the normal bundle of this one manifold. Okay, fine. But the last piece of data, and that's somehow the interesting one here, is a homotopy. If I have a trivialization of the tangent bundle, well, the tangent bundle plus the normal bundle at this point on this one manifold is, of course, just the tangent bundle of R2, because this diagram was embedded in R2. So this is sort of a canonical isomorphism between these two. But now I've also picked a trivialization of the tangent bundle of this one manifold and a trivialization of the normal bundle of this one manifold, which gives me a trivial two-dimensional bundle. But then my R2, it's really a sort of canonically chosen R2. So this has a canonical sort of trivial framing. The tangent bundle of R2 is sort of canonically identified with the trivial bundle on R2. So I've sort of suddenly, at this point, I've sort of produced two framings of R2. And I have to ask that these two framings are the same, but I have to ask them to be the same in a sort of homotopically correct way, so I have to record a homotopy between these. And this homotopy... they don't have to be orthogonal or anything. So it is essentially a rotation. It's like a path which moves from this one framing to this other framing. So it's precisely at every point you have the sort of background framing, but then you have an interesting framing that you've sort of picked by these two pieces of data, and then you have a particular rotation, which tells you how to rotate this sort of particular chosen framing back to the sort of blackboard framing. That's right, but you have a path, and well, either you chose them orthogonal, or otherwise you say you have a path in GLN. So it's not just a rotation; it's also a sort of you can So you have a path in GLN between these two things. And GL2, yeah, exactly. Okay, and this guy is of course what doesn't work for the circle. So for the circle standardly embedded in R2, you won't have this piece of data, and that's precisely somehow a geometric reinterpretation of this picture here. What happens is if I start here with sort of a point with the trivial path in GL2, once I've sort of went all the way around it, it will have picked up the path which rotates sort of 360 degrees, and that's just, there's no you can't trivialize that guy. Okay, good. So that's sort of the idea what the graphical calculus is in a rigid monoidal category. Let me sort of introduce the following notation, which is pretty useful, is if I have an object in a rigid monoidal category and a one manifold equipped with all of this data, then I can write sort of an integral sign and think of sort of I integrate this object over this one manifold. This is of course just notation. Of course it's motivated notation, but a priori just notation to mean the induced scalar in this monoidal category. So it's an endomorphism of the tensor unit, which is in this sense the trace, or a trace if I'm using a circle, which I can't, right? And the other comment is, of course, this works not just for R2, this works sort of more generally in any frame 2 manifold, right? Here you could say, okay, if this is some 2 manifold, M2, I could still sort of, if this has a framing, I could still ask for this piece of data. And that, of course, is important later if you want to build topological field theories out of these categories. Okay, so that's the sort of idea. So then let's sort of go back to our original situation and let's look at our object. Now I can do something like I can think of what's this object evaluated on S0. That's precisely this guy X tensor X dual. And what's this object evaluated on the one disk? That's this evaluation morphism that we've drawn. Okay, and of course, we don't necessarily have a morphism back. However, and now sort of I'm going to move into the semi-simple world. If C is not just a monoidal one category, but if C is a fusion category means it's a semi-simple category. It has a finite number of simple objects and the tensor unit is simple. Right, let me sort of also introduce the following notation. I will write pi0 of C for the set of simple objects up to isomorphism. This sounds a bit fancy now, but this will also come in handy as a piece of notation. If I'm in this situation, then it turns out that an object X is simple. You can sort of easily check this, if and only if the tensor unit appears precisely with multiplicity 1 in X tensor X dual. So if I take X tensor X dual, those are two simple objects, tensor them together, I get sort of fusion rules. If the tensor unit appears with multiplicity 1, then the object is simple, and this is an if and only if. Yes. For example, yes, exactly. In this setting, you could say simple means, so once you're in the semi-simple category, you're simple if and only if your endomorphisms are, in this case, I'm working over an algebraically closed field, so this is why this works. Its endomorphisms are just the complex numbers. Yep, that's exactly right. Okay, and in this case, what happens is that this evaluation map is precisely the projection to this one, so just sort of is a choice of projection to this one dimension, to this sort of factor 1 that appears in this direct sum decomposition. But then, of course, if I'm in a semi-simple category and I have this projection, I can just split this projection. I can just find an injection going back that splits out this one. So I can just choose a unique map, evaluation X, that I call sort of evaluation X stagger, which goes from the unit to X tensor X dual, so that if I go sort of around the circle, I get the identity. So in pictures, this is this equation. In a way, yes. Yeah, so I should give you, so yes, I'm just suppressing a lot of data when I'm writing this. That's basically the answer. So yes, you should record the direction, and you should also record all this framing data that I was talking about. And I'm just not doing this anymore now. But from sort of the previous discussion, if I'm drawing this picture, you sort of know what I mean. Okay, so there is sort of a piece of, I mean, first of all, yeah, okay, there is a sort of useful, sort of intuition for this, I think, is one could think of this object as not just being this object X a priori. I said, you can sort of evaluate it on all one manifolds if I want to. But there is a way to think of this as sort of pretending that you can actually evaluate this object X on two manifolds as well, or at least on some two manifolds. That's of course not completely correct, and you can think of this as some sort of extra fractional dualizability, but it's quite useful to think of this equality as being somehow the value of X on the two disk. So the two disk is what sort of trivializes this circle. And this is the value of X, it's on a circle with a sort of framing which is a bounding framing, which is a framing induced from sort of it bounding the two disk. So this is something you wouldn't a priori be able to do in just a rigid monoidal one category, but using semisimplicity and making this choice, you get this additional sort of freedom to draw string diagrams which are defined on manifolds that have sort of less framing data or are less rigidly framed. That's sort of the whole idea here. And so, yeah. Yes. A framed disk, but a two-framed disk. Of course, sort of a framed disk, yes. I think of this as a framed disk. Exactly, with the standard framing. But sort of as a consequence, I think of the circle now not as tangentially framed, but as tangentially two-framed. So I've sort of given myself a little bit extra framing, and that allows me to now draw circles. That's just an interpretation of the story. And this leads to a canonical isomorphism from the left dual to the right dual, but this isomorphism, of course, is usually not monoidal. And a monoidal such isomorphism, as we've seen in Christoph's talks, would be called a pivotal structure. So you can think of this data and this whole discussion here as just another way of saying what Christoph said yesterday, is that the Nakayama functor in a semisimple category is trivializable. And here I'm saying sort of if you make some normalization choices, there is a canonical trivialization of this Nakayama functor. I think this is basically an equivalent interpretation. Okay. But not monoidally, of course. Okay, and so now we can move on to the S-matrix. So if I have not just a monoidal, a fusion category, but if I have a braided fusion category, so a fusion category in which I now can also sort of move objects around one another. So now I have lines in three-dimensional space that I can work with. Then I define the framed S-matrix as basically this sort of Hopf link. Now it's the classical Hopf link of two lines which sort of evaluate in three-dimensional space. But again, a priori, I couldn't draw these circles in a fusion, in a braided monoidal one category rigid. But if I use these choices, these sort of fake framings, I do get a well-defined number like this. I think this is originally due to Pavel Ettinghoff, I think, this way of constructing the S-matrix. And for those of you who know ribbon categories, who know braided fusion categories with a ribbon structure, this is related to the usual thing you would call the S-matrix. Namely, if C is a ribbon category, then the usual S-matrix is sort of the dimension of X times the dimension of Y multiplied by this thing. So you can think of this as a rescaling, a renormalization of the S-matrix, but it's very useful because this doesn't depend on any of the additional structure. This doesn't depend on the ribbon structure. This is a thing which is just defined for this braided fusion category, and this other thing sort of depends on the pivotal structure by these additional scalars. Okay. And then there is a big theorem that's due to many people, sort of different versions of it and different variants. So I don't know whether you can find this statement anywhere in the literature, but you can certainly plug it together from statements in the literature, which is that this S-matrix is invertible as a matrix if and only if, right, this S-matrix is a matrix which goes from the set of simples up to ISO times the set of simples up, sort of it pairs simples up to ISO. This is invertible if and only if the so-called Müger center of this category is trivial. The Müger center is the subcategory of transparent objects. It's the objects X and C that braid trivially with every object in the category. And this is true if and only if the C is invertible up to a certain form of Morita equivalence, up to the correct notion of Morita equivalence for braided categories. So I'll say a little bit what the TQFT interpretation of this condition is in a second. But if you're familiar with sort of these higher Morita categories, then you will know what this notion means. And otherwise, just sort of take it on faith that there is a notion of Morita equivalence for braided fusion categories. Okay, and this statement is really, really powerful because it essentially relates something four-categorical to something one-categorical and actually to something zero-categorical, right? This is a higher four-categorical statement, and this is just a statement about a particular matrix. This is a matrix being invertible. This is something you can do in linear algebra, and this is something you need some development of four categories for to understand. So it's quite a powerful statement. And I should also say, maybe you're familiar with this terminology of modular categories. This is precisely the categories B for which this S is invertible. Those are essentially modular categories. A modular category is a category where you're not on framed manifolds, but on oriented manifolds. So it has this additional ribbon structure. But then it's one of these conditions. So the important part, if you ignore the orientation, the important part in a modular category that distinguishes it from a sort of general braided category is precisely this condition, this non-degeneracy condition or modularity condition. So why are modular categories interesting? Because they appear in three-dimensional anomalous TQFTs. And this we can understand from the perspective of this theorem. So let me sort of also give you sort of a little overview of that story. If I have a braided fusion category B, this leads to a framed, fully local or fully extended four-dimensional TQFT together with a three-dimensional boundary theory. Now, this four-dimensional TQFT, the sort of partition functions, at least, of this four-dimensional TQFT were originally constructed by Crane and Reutter, and is also known in physics as the Walker-Wang model. And the three-dimensional boundary theory is essentially the Reshetikhin-Turayev TQFT constructed from a modular category, which really lives on the boundary of this four-dimensional theory. And moreover, you can actually recover B, this category, as the category of line and point defects or operators in the boundary theory. So you have this boundary theory, and you could ask, okay, what are sort of the lines and defects that live in this boundary theory? And this recovers my original braided fusion category B. Yes. If you use, depending on which of the modular categories you're using, it's more or less, it's sort of the non-perturbative version of Chern-Simons theory. Yeah. But this works sort of depending on the input, B. Yeah. But it's certainly the right way of thinking about this. Yeah, okay. I come to this. I'd say it's the anomaly of Chern-Simons theory. So let me sort of, so far I've just used the braided fusion category. Now let me sort of talk a little bit about invertible TQFTs. Namely, what will turn out is that this 4D theory is an invertible theory. An invertible TQFT is one where essentially somehow the intuitive definition is its values on all manifolds is invertible. So this means that if I have a top-dimensional Bordesson, it gives me an invertible linear map. But also if I have a vector space, it's an invertible vector space, so it's a one-dimensional vector space, it's just a line. And sort of everything inside is invertible in as many ways as you can think of. And of course, I'm being sort of a bit imprecise what I mean by a TQFT here. But for every definition of TQFT, you can come up with a notion of what it means for this to be invertible. And it really means make everything inside invertible. And I say that an anomalous n-dimensional TQFT is a boundary theory of an invertible n+1 dimensional theory. This is sort of matches up with examples, and I think this perspective is due to Dan Fried. And it really comes from, I mean, a reason this really sort of works and makes sense is that invertible theories are usually classical Bordesson invariants. So up to sort of, depending on your targets and so on. But essentially, you should think of this as invertible theory as just recording something like signatures and Euler characteristics. And so if you're on the boundary of such a theory, you're more like a sort of projective three-dimensional theory. So some of the functoriality is twisted a little bit by these invariants of this top-dimensional invertible theory. So anomalous n-dimensional TQFTs feel a lot like just plain n-dimensional TQFTs, but really they still live on a boundary of this n+1 dimensional theory. And an interpretation of this S-matrix theorem in the language of TQFTs then is that B is non-degenerate, or the S-matrix of B is non-degenerate, that's what it means to be non-degenerate, that's the definition, if and only if this four-dimensional bulk theory is invertible. In other words, if B defines an anomalous three-dimensional theory. So the moment you have a B, which is not just a braided fusion category, for a braided fusion category, this 4D theory is also not invertible, and there's really more like an open-closed thing going on. You have a bulk theory and a boundary theory. The moment you make this B non-degenerate, the bulk theory becomes invertible, and then you can think of this boundary theory as it behaves almost like there wouldn't be a bulk theory. You'll only see it if you really sort of look at, say, representations of mapping class groups, where you suddenly get a projective representation, which is sort of twisted by this invertible 4D theory, which is still there. It's not gone. Okay, so that's the one categorical story, essentially. And what I want to do now is to sort of build on this and think about this in higher dimensions. But first of all, are there any questions about this part of the story? Okay, then let's just move up in dimensions, and let's just move up to arbitrary n. So what I want to talk about now is, okay, what should this notion of a braided fusion category be replaced by if I don't want to build three-dimensional boundary theories or four-dimensional bulk theories, but higher dimensional things? And sort of a slogan that's very useful in this story is that multi-fusion one category, let me say a little bit what I mean by multi-fusion. Multi-fusion is just the same as fusion, but if I drop the condition that the tensor unit is simple. Right? Fusion, I said, you're a semi-simple category, finitely many simple objects, you're rigid, and the tensor unit is simple. If you drop the tensor unit being simple, that's usually called multi-fusion. Sort of a bit of a bad notation because this one should be more natural and this one should be sort of more specific because it's one condition more. But I think that's just sort of a historic accident. And you should think of as a multi-fusion one category as sort of a categorification, a one-dimensional higher version of a semi-simple algebra. So multi-fusion one category is a sort of semi-simple algebras on steroids, if you want. And similarly, you should think of a multi-fusion n+1 category, whatever that is, as analogous to a multi-fusion n category. And if you take this slogan, you get sort of an inductive definition out, and that's what I want to sort of recall. A fusion one category, oh, you mean down here, is sort of a division algebra, I would say, or a simple algebra. Debatable, there's subtlety, but I'd say that's probably the best interpretation. Yeah, it's sort of a simple, okay. Here's the definition. I don't want to sort of spend too much time on the definition. If you're familiar with sort of some of this language, it gives you some idea of what I'm working with, but otherwise we can also just sort of in a second just work with the string diagram graphical calculus. So the definition is that a multi-fusion n category is a C-linear monoidal n category, so now I can draw diagrams in n+1 dimensional space rather than in 2 dimensions, such that it has direct sums, so there's a notion of direct sum, that's pretty easy to define, and all n idempotent splits, so this is the only part I'm going to talk about is n idempotence. This is a whole story and it's really interesting. And essentially the idea is that if you have an object in this TFT, which is say some brane or some defect, you can sort of try to construct other defects from this object by a construction which in condensed matter physics is called condensation. It's also sort of known under the name of orbifold completion or orbifolding. I mean, orbifolding is in particular an example of it. Generalized orbifolding is another name for this. And it's essentially sort of branes or defects that you can build in some controlled way from this other brane or defect. And one of the conditions is this all n idempotent split is essentially saying all theories or all sort of defects that you can build from one of these defects is already in your category contained. So this is really just a completeness condition. This is like if you ask your Hilbert spaces to be Cauchy complete. You want to have sort of all of these things already in there. So let's sort of forget this condition and think of it as a certain completeness condition. I do also require, and this is somehow the inductive part, for every x, the endomorphisms of x. This is supposed to be a multi-fusion n-1 category. So this is really where the meat of the definition is happening. I require it to be rigid, and I require it to be finite, and finite means that a certain set is finite, and I'm going to define the set on the next slide. So if you unpack this for n=1, you basically get a version of the definition of a fusion one category out. This is a way to define a semi-simple category. You have ordinary idempotents, they need to be split. You are locally, the endomorphism of every object is a semi-simple algebra. You're rigid and you're finite. Okay. And in a multi-fusion n category, there's a proposition you can prove that an object X is simple, and this goes back to your question earlier for fusion one category. The same thing still works. An object X is simple if and only if it's indecomposable under direct sums. If and only, now you can't just look at the endomorphisms of the object, but you have to look at the endomorphisms of the identity of the identity of the identity. You have to get all the way up until you get to vector spaces, and then you ask that to be one-dimensional. So on this object, if you think of it as sort of as a sheet or a higher dimensional manifold, there are no point operators. That's sort of the idea. Okay. So now you could ask, okay, how much does such a multi-fusion n category or a semi-simple n category behave like a semi-simple one category? And the first thing that happens in a semi-simple one category is Schur's lemma, which says that if I have two objects which are simple, and if there's a non-zero morphism between them, then they're actually isomorphic. Okay? And already in the semi-simple two categories, this doesn't work anymore. For n=1, you're connected in this sense, if and only if you're isomorphic. For n2 or higher, that's not true anymore. If you're isomorphic, of course you're connected. There is an isomorphism between you. But it's not true the other way around. You can have non-zero maps that aren't isomorphisms. However, there's something which is still true, which is a bit like Schur's lemma and gives you sort of a lot of traction about these categories, which is that having a non-zero morphism between two simple objects is an equivalence relation. No, they're not. So you can ask for, right, when I say isomorphisms, I mean equivalences. Yes, sorry, yes. So when I say isomorphism, I mean equivalences in a higher categorical sense. But these maps are really just non-zero maps. So they don't need to be equivalences. However, this still turns out to be an equivalence relation. So if I have a non-zero map from X to Y and a non-zero map from Y to Z, I can compose them. And a non-trivial statement that's really only true in a semi-simple world is that this is again a non-zero map. So non-zero maps compose to still give you non-zero maps. And so once you have an equivalence relation, you can make a definition. You can define the quotient of the set of simples by this connectivity relation. And that's what we call the Schur components of this category. And that's interesting because that's a much coarser equivalence relation than equivalence. So of course you have the equivalence classes of objects, but now you have this much, much smaller set, this sort of much coarser quotient, which is simples up to Schur connectivity. And it turns out that this set actually behaves in the semi-simple context much, much better and much, much more like the set of simples up to isomorphisms than the set of equivalence classes of simple objects. So in many respects, this is sort of the better set of simples. Okay, let me sort of give you just a quick example of a fusion 2 category just to get some idea of what's sort of going on, of what structures we're seeing. For example, you can look at the 2 category. It's a monoidal 2 category of semi-simple superalgebras over, say, the complex numbers. So objects are semi-simple superalgebras, morphisms are super bimodules, 2 morphisms are bimodule maps. And now let me just sort of write down what are these simple objects, what are these simple 1 morphisms, and so on. So what we're seeing here is that we have 2 simple objects. The simple object is precisely the trivial algebra and the Clifford 1 algebra. Those are both simple objects. Those are sort of the equivalence classes of simple objects. So equivalence in a higher categorical sense, they're precisely 2 of these. But there is a non-zero morphism between them, namely the Clifford, the non-trivial morphism between them is Clifford 1 as a bimodule over Clifford 1 and C. And that's a non-zero morphism between them, which isn't an equivalence. Yes? Yeah. Right, and so this is sort of the structure of this category as a semi-simple 2 category. And of course, we know there's also fusion rules there if you want. If I tensor Clifford 1 with Clifford 1, I get something which is equivalent to the trivial algebra. That's essentially Bott periodicity of complex superalgebra. So those are sort of the fusion rules of this fusion 2 category. And what you should notice is that these objects are inequivalent, but yet they are connected. They're in the same component, so there's just a single component. So pi 0 of superalg is trivial. So this would count as a connected fusion 2 category in this language. And that's quite helpful, and this sort of somehow captures the fact that you can get the Clifford algebra 1 by just looking at this object and its endomorphisms, because of course it's an algebra object in here. You can sort of recover this algebra from an algebra in here, this other object. That's sort of the idea. Okay, so let me give you some examples. So a sort of typical slogan of what fusion categories are, what fusion categories are good for, is that fusion categories are a sort of generalization of finite groups. This actually, you can sort of everything you can do in finite groups, you can do with fusion categories, because for every finite group, you have a particular fusion category that essentially behaves like this finite group, and this fusion category is the category of finite dimensional G-graded vector spaces. Okay? Sorry? G is a finite group, yes. And of course, that's really like fusion, in all the semi-simple fusion world, it's really only about finite things here. And a fusion n category, in the same sense, generalizes finite n groups. What I mean by finite n group, one way to define it is to say it's a loop space, all of whose homotopy groups are finite and which only has homotopies up to a certain level. And indeed, for every one of these finite n groups, you do get a fusion n category, which you can think of as sort of G-graded n vector spaces, if you define it correctly. And the slogan, therefore, you could think of as saying higher fusion category theory is sort of a common generalization of finite dimensional linear algebra. I'm sort of linearizing everything appropriately, and finite homotopy theory. So homotopy theory, where I only have finitely many homotopy groups and they're all finite. So yes, so you will have, so what you will have, you can look at the sort of the n vector space is created by a finite n group, and you can also look at representations of a finite n group, and those should sort of be Morita equivalent. So there should be a sort of Morita equivalence between these, similar to the one categorical setting. Okay. So what I should say, however, is that so this sort of, first of all, it suggests that you can sort of start bringing in notions of finite homotopy theory, and we've already sort of done so by looking at a set of components. What I should say is that this n vector here, the vec G, of course, G, you can recover it fairly easily as a set of simples up to isomorphism. Up here in these sort of higher dimensional versions, what will happen, and I can just sort of tell you, is that you will produce by sort of linearizing, by this sort of higher categorical version of linearizing, you will suddenly produce many, many new objects and many more new morphisms. So for example, there are simple objects in here which are not invertible. There are morphisms in there which are not invertible. So you produce many new objects and many new morphisms. And it's almost like you can't really recognize the original n group anymore after you've done this linearization. Then you get something new. So right, exactly. If you take n vec G, you start with G, you take n vec G, and now you take only the invertible elements, and you get a new n group, which is not equivalent to G. That's exactly right, which is really weird. And you get very interesting things out of this. I mean, you get things like Brouwer groups and so on sort of come in on top of that by this linearization. However, you can recover the homotopy groups of your original finite n group. And this is precisely sort of by this definition where I'm defining, okay, if I have this fusion n category, I can look at its loops, at its sort of loop space or loop category. I define the loop category to just be the endomorphisms of the unit, and I can do this k times if I like. And then I can look at the components of this guy. And that I could call, just sort of makes sense, it's a definition pi k of my fusion n category. And this pi k is a good notion because this precisely recovers the homotopy groups of G. And here you see exactly the difference. If I just look at the invertibles in n vec G, I don't see this equivalence relation anymore because I've thrown out morphisms that are non-zero but not equivalences. So you don't see this equivalence relation anymore. So you really need to remember the non-zero maps as well, not just the equivalences, to recover the homotopy groups of your G. And so indeed, these pi kc, this is something you cannot define for just a general monoidal n category. This only makes sense for these semi-simple monoidal n categories. And they behave a lot like the homotopy groups of a space. And in fact, they are not groups, so they don't have a group structure in general, but what they do have is a structure of a certain kind of fusion ring. So I can write down the definition later if you're interested, but there's sort of a certain sort of fusion ring structure you can define on these pi kcs. And if you come from a group, this fusion ring structure actually becomes a group structure, and it is just the usual group structure of the homotopy group of this original G. So you have now this sort of weird world where you have sort of mixed linear algebra in some way with finite homotopy theory, and you get sort of generalizations of homotopy groups and so on. So it's sort of, yeah. No, this is also simple modular connectivity. So this, then you get precisely what Zhengzheng was saying, that you can take whatever your category is, and you can just look at the sort of maximal groupoid, all the invertible objects, all the invertible morphisms in there, and that's another space, and then you get the homotopy groups of that space. But that somehow wouldn't recover the original homotopy groups of this thing you're linearizing. This would sort of mix it up with all sorts of sort of Brouwer group-like things. There are more fusion categories, because for every group, or for every finite n group, if I understand your question correctly, for every finite n group, you do get a fusion n category, but not the other way around, because you do have examples of fusion n categories where the pi kcs are no groups, right? That's a way to recognize, or that's sort of a necessary condition for coming from a group, is that your sort of homotopy sets pi kc form a group. But there are examples where they don't form a group, where they form a fusion ring, and then you can't come from a group. Exactly. Okay, so now we want to work with these structures, and we want to sort of draw pictures and draw diagrams, right? And previously I've talked about these diagrams. Now I again want to draw diagrams. Of course, how do I draw n-dimensional diagrams? Well, I can't really draw them on a blackboard, and I can't really draw them in pictures, but I can describe these diagrams geometrically. And that's sort of why I went through this exercise earlier for these monoidal 1 categories, where it was really a bit of an overkill to start describing these diagrams. Now we can actually sort of use this perspective, and this is essentially sort of coming from the cobordism hypothesis, to actually sort of still talk about diagrams in these categories by using this Tangle hypothesis, or using the cobordism hypothesis. And the statement is the following: if I have a monoidal n category, like a fusion n category, but this works for general monoidal n categories, and I have an n minus k morphism, which is fully dualizable. I won't say what this means, but this is just sort of the correct analog of being sort of what happens in, for example, in a rigid monoidal n category. Then I can evaluate this on an embedded k-dimensional manifold in n+1. With framing data, and this framing data is now analogous again, I have a tangential framing. I have a trivialization of the tangent bundle. I have a normal framing, a trivialization of the normal bundle, and I have to have this homotopy filling this triangle. So all I'm saying is, again, if you're careful how you sort of draw your pictures, you can now draw the sorts of string diagrams you would imagine in n+1 dimensional space and evaluate them to numbers in a fusion n category. Okay. I won't say too much about the slide because it's basically a version of the slide we saw in the beginning, and it's telling you precisely what additional decorations I have to sort of put on these string diagrams to make them well-defined. Yes? So, right, okay. So yes, no, you're right. The way I wrote this slide, let me a priori say a fully dualized can be evaluated at a closed embedded K-manifold, then it's this data. If the manifold is not closed, you have to make sure you have to really implement it as a Bordism. You have to say what's the source, what's the framing data on the source, how is the framing data compatible, so you get all these compatibility conditions in. So these conditions is really if I just want to draw a closed diagram. But of course, later on, I'm not going to just draw closed diagrams, and I'm sort of sweeping all of this under the carpet. But yes, you have to be careful with this again. Okay, and again, this all this data, if you have this also allows you to draw defects on any framed n+1 manifold W. It doesn't need to be Rn+1. Okay, so let's get going. Let's just do the same story again that we did in the one categorical case. So suppose you have a fusion n category and you have an object in loops n-k in C. And what I can do is I can take this object and put it on a sphere. And I can put it all the way on a sphere. Let me just sort of put it on a high enough sphere that I end up at the level which is one level below partition functions. So it's one level below numbers. And this is some object in loops n-1 of C. Loops n of C is just the endomorphisms, the iterated endomorphism of the tensor unit, so that would just be the complex numbers, but this is now some category. And I do have an evaluation morphism from this object in this category to the unit, which looks like a disk. All right, so this is again the same story. Again, I should sort of denote there's more framing data here in this notation, but you do have this nice disk. But now in our setting where I start with a fusion n category, this thing is just an ordinary fusion 1 category. We know how to work with fusion 1 categories. In fact, it turns out that this object X is simple in the n categorical sense, or this sort of endomorphisms of some tensor unit is simple if and only if I'm looking at the sphere, I have 1 appearing precisely with multiplicity 1. So it's the same story as we did in the one categorical case. And so I can again find sort of a map which goes the other way, even if the sphere doesn't admit a framing, by just splitting this projection. So in other words, there is a way to trivialize the sort of higher dimensional Nakayama in the semisimple setting as well, if you want. And again, I think of this sort of equation of this sphere with this red dot being 1 as a sort of one higher dimensional disk in a way that wouldn't work if you just use the Tangle hypothesis. So now I can place this object X on a sphere with a k+1 framing rather than just a k framing, for those of you who know the cobordism hypothesis. If you, otherwise just think of I'm doing some black magic here which uses semisimplicity, which allows me to evaluate objects on spheres, which is something a priori I couldn't do if the sphere wasn't framed. That's the idea. And this really needs semisimplicity, because otherwise, again, you can only do it if the sphere is framed. This question, yes. Oh, so if I'm in any semisimple category and I have an object which has, okay, so you take this object, it's built in some complicated way, but it turns out to be of the form 1 plus some other objects, and 1 just appears with multiplicity 1. If you have now any non-zero map from this object to 1, you can think of this as part of a projection to 1. And you can just normalize away a map going the other direction. That's just how direct sums work, right? So if you're, you just pick any map, any non-zero map back, and then if you compose them together, you get some non-zero number, which you can divide normalize by. So this is just sort of the magic of semisimple categories. It essentially comes down to Schur's lemma. Okay. And this is something that, of course, goes sort of horribly wrong in a non-semisimple category. Like, you certainly couldn't find such a splitting, and in general, you can't. Okay. So now that we have this, we can sort of go on and define this pairing again. We take an x in omega kc and y in omega n minus kc, assume those to be simple, and we define this pairing by taking a sphere and another sphere that are sort of the right dimension, so that if I link them, they are sort of linked precisely in dimension n plus 1, sort of the dimension in which they link. And I can define this pairing. And again, I have to use these sort of fake framing things down here to make this, to be able to evaluate these objects on spheres. Okay. And now it turns out, and this is a non-trivial statement that I'm going to sketch a proof of, that this matrix, which is defined for sort of something at level in omega kc and something in omega n minus kc, only depends on components. So a priori, it's clear that it only depends on equivalence classes of objects. And in the fusion 1 category setting, or in the Pareto fusion 1 category setting, that's all we needed to prove. We needed to prove this is independent up to isomorphism. But now we have to prove something stronger. We have to prove this is actually independent up to component. And only then does it become an interesting pairing, because again, the equivalence classes could be really, really large. There are examples of higher fusion categories where you have infinitely many equivalence classes of simple objects, but only finitely many components. And so this is really important to get down to some finite matrix. And here's sort of a proof sketch. Oops. So suppose you have two simple objects that are in the same component, so that are connected by some non-zero map between them, by some sort of codimension 1 relative defect. Then pick some simple map between them, which goes from x to x prime, which is non-zero. It doesn't need to be an equivalence, just some simple map. And first, let's sort of record some things that we know. First, if I evaluate x on the sphere, I've made this choice here to normalize this precisely to 1. That was sort of the definition of this little dot down here. Now I can do the same for f, but sort of relative on this sheet. So I can again find a little one of these dots, so that I can just sort of create a bubble of f. Now I can move this bubble around and I get sort of this picture. I can't do much more with this for now because here I'm sort of stuck. I have this sort of complicated thing down here, which is some complicated framing information. Okay. This step. This one. This one. Oh, I'm doing the same. So this is the same trick that I did before. I look at the evaluation of f. Since f is simple, you will find a splitting of the evaluation map. So it's the same trick, just sort of relative to the blue sheet. Exactly. So you can do it again by semisimplicity. Okay, so now, however, so it turns out that sort of this is 1, and it turns out that this is 1. But we've already found a splitting of this disk, right? We've already defined this guy to be the splitting of the disk. So now we have two different splittings of the disk, right? If I compose this with the red disk, I get 1 by definition. But also if I compose this guy with the red disk, I get 1 by this equation. So it turns out that those have to be the same, because there's a unique splitting if there is a splitting, because it's just a one-dimensional Hom space. And so indeed, it turns out that this is equal to this. So now let's sort of look at the Hopf link. So now I'm looking at a Hopf link of a, say, a green loop with this guy. I create this F bubble. I move this F bubble around. The reason I can move this around is that this sort of F loop here, and Y, they don't link anymore, because those are sort of dimensionally not sort of linkable anymore. So I can just move this around. It doesn't interact at all with this Y loop. And now I can just look at this bottom part. I can't look at the whole thing, of course, because this is now linked, doesn't look like this anymore. But by the uniqueness of splitting, I already know this sort of local equation. And I can apply this local equation here and get that this is equal to that. So really, this pairing descends to the components. And that's really important, because only there does the pairing get non-degenerate. Before that, it wasn't non-degenerate. Okay. And I've tried to make the point earlier that you should think of these fusion n categories as sort of generalizing finite homotopy theory in a way. And if you like homotopy theory, you could ask, okay, what is this pairing then? What does that mean? And it generalizes the Whitehead bracket. So you can define in a loop space, you can define a whitehead bracket going from pi k to pi n minus k to pi n, and that precisely sort of, this construction here is a way to generalize this whitehead bracket to these weird semi-simple things, which aren't quite spaces. So if my fusion category is linearized from a space, then this recovers the whitehead bracket, this pairing. And of course, sort of, the reason it goes to the complex numbers is that I'm sort of have explicitly trivialized the endomorphisms of the tensor unit all the way up. Okay, good. Are there any questions up to sort of on this slide? That's right, of a loop, yes. Yes, because this, so if I take a loop space and I linearize it, then I have this fusion n category. And now I look at the sort of Schur components of that. That recovers the homotopy groups of the original space. Well, in the original space, if you just take the original space, if you have a non-zero map, you have an equivalence because all the maps are equivalences. And what the linearization is doing, it throws in a bunch of new objects. For example, I mean, you can get this by linearizing just the CMOD 2 at a certain level. So you throw in something like the Clifford algebra, but you remember that it was thrown in because there is a bimodule between these, because there is a map between them. And this sort of component thing sort of collapses everything that you've thrown in by hand to linearize it, to make it fusion, and brings it down to something which is still sort of where you really see the original sort of core. If you forget the non-zero maps, as Cheng was asking, you would sort of, in this example, you take superalgebras and just look at the Picard groupoid of superalgebras, and then you see another CMOD 2 appearing. You don't see that there's a connection anymore between these, because now this is not invertible, so you forget this in the Picard spectrum, and suddenly you have two different objects appearing here. Okay. Okay, so let's again sort of come to this S-matrix theorem, and as before, there was sort of this interpretation of this S-matrix theorem in terms of TFTs. Let me sort of first give you now the same interpretation. If I take a fusion n category which is separable, this is a technical condition that I won't comment on too much, but there is a conjecture which is saying that which is true for fusion 1 categories, which is saying that you're always separable if you're over a characteristic zero field. We don't yet know how to prove that, but so I expect this is not a condition. We can just cut this out, but let's sort of have it in there for now. If I have a separable fusion n category, this leads now to a frame fully extended or fully local n+2 dimensional TFT with an n+1 dimensional boundary condition. So this just generalizes the situation we've seen before. You should think of this bulk theory as basically sort of remembering the Morita class of C. If you have two things that are Morita equivalent, these bulk theories will be the same. And its boundary theory really remembers C itself. So this remembers C up to isomorphism rather than up to Morita equivalence. And moreover, you can recover C, and there you see that you need the boundary theory for this, as the category, the n category of boundary conditions of this boundary, of defects in this boundary condition. And this is the n category of now codimension greater or equal to 1 defects, an operator. Sort of the objects are codimension 1 defects, and so on and so on. Okay, so that's just sort of for a bit of a perspective. And then the theorem is the following. This S-matrix for all k, so suppose this S-matrix is invertible for all k, so there's not only one S-matrix, there's an S-matrix for every k, because I can pair sort of complementary dimensional operators. If this is invertible for all k, this is equivalent to the Drinfeld center of my fusion n category being trivial, which itself is equivalent to the category C being trivial up to Morita equivalence, which of course then is equivalent to saying that the bulk theory is invertible, which is equivalent to saying that C defines an anomalous n+1 TQFT. So these fusion n categories for which all of these matrices, all of these sort of n+1 matrices are invertible, those you could call modular n categories, or maybe non-degenerate fusion n categories. And this proves the conjecture in condensed matter theory. Okay. Yes, and you can, so here I'm talking about fusion n categories. Previously I've talked about braided fusion 1 categories. You can embed sort of the world of braided fusion 1 categories into the world of fusion 2 categories by just going to the modules. And then the Drinfeld center of modules contains the Müger center, and indeed triviality is in this case equivalent. The triviality of the Müger center for braided fusion category is equivalent to triviality of the Drinfeld center of the fusion 2 categories of modules of that braided fusion category. So you can generalize somehow this Müger center statement to a Trinfeld center statement. This is a technical question, exactly, but the way you can handle, I mean, I think, as you also mentioned in your talk, the best way to handle it is to define it as AA bimaterial maps from A to A. And that you can do using the framework. I mean, in our case, we're sort of using infinity n categories to describe these n categories, and there you have sort of your operats, which encode what it means to be a bimaterial map. And then you can define the Trinfeld center in this way. Yeah. Okay, and so the sort of slogan, the conclusion is that if I am in a semisimple anomalous TQFT, there is this perfect pairing between operators of complementary dimensions. So you can really pair these operators up perfectly. And now let me sort of make a comment on this, because I still haven't really, I mean, the way sort of if you read or if you hear this talk, the way you interpret semisimple anomalous TQFT would be a TQFT which comes from these higher fusion categories. But this statement is actually much more robust than the theory of higher fusion categories. So even if you don't believe in higher fusion categories and if you don't like higher fusion categories, the way we prove this is actually not by looking at extended theories, but you can already prove this as a completely non-extended level. So if I have a non-extended semisimple open-closed TQFT, the statement is still true. So I really need just a bulk theory and a boundary theory. The trickiness here is to identify what the S-matrix is in terms of the semisimple non-extended theory, but there's a more general statement sort of going on in the background, which works even if you don't believe in fusion categories and higher fusion categories. And there's an expectation, certainly, that some of this should also work for non-semisimple and non-compact theories, or theories where defined non-compact in this TQFT world, I mean, it's not necessarily defined on all top-dimensional manifolds. In both of these settings, the trickiness is to figure out what to replace this set of components, this pi kc by. What is sort of, it won't be a matrix with a sort of between two vector spaces with a chosen basis, but there will still be some linear map, and you have to figure out what the vector spaces are. And sort of a question I have in general is, in how far is there a sense that you have these pairings for more general types of TQFTs, or maybe for more general types of QFTs as well? So it's really the sort of a way to discover what these components are here is a way to see when is this statement true. Like, what do you need to do to make this statement true? You really have to pass to these quotients. And it would be interesting to see, is there some sense in which this pairing between operators and complementary dimensions, and if I'm in a general QFT, I can still pair topological operators in that way. Is there some sense in which I can pass to a certain type of quotient where this pairing becomes invertible? Or maybe I have to start pairing non-topological operators, I'm not sure. So that's sort of a general question I have. How far is this something that should be sort of generally true about all kinds of TFTs? Or is this only true for these sort of very particular semi-simple ones? Okay, so let me wrap up with some consequences. First, for example, you get things you would see sort of from modular categories. You get a higher Valinde formula, for example. So if I have objects in pi k of c, I can compute these fusion rules on pi k of c. I was saying that pi k of c is sort of a fusion ring. There's a sort of normalized fusion rule for these. And this is computed in this way. So if you're familiar with the Valinde formula, you will recognize this. If not, you can ignore that part. Interestingly, the sum here is not over operators of the same dimension, but over operators of complementary dimension. So the Valinde formula now really sort of tells you what are the fusion rules of pi k by sort of summing over operators in pi n minus k. And this, of course, is again powerful because you can recover fusion rules from the S-matrix. Potentially powerful. I haven't done this in any example yet. But also, and this is what we've used it so far, is that it tells you a lot about the sort of the structure theory of higher fusion categories, but also of ordinary fusion categories and ordinary braided fusion categories. So for example, an easy consequence of this S-matrix theorem is that if I have a Morita invertible category, the S-matrix is invertible, but the S-matrix is a priori not a square matrix. It pairs pi k and pi n minus k. So a necessary condition for this to be invertible is, well, the sizes of the two vector spaces, the dimensions have to be the same. And this tells you, well, okay, if I have, this tells you can understand how many components of operators in dimension k you have if you know how many components of operators in dimension n minus k you have. For example, if C is Morita invertible and a fusion category, which means that pi n of C you don't have local operators, then this implies that pi 0 of C is trivial. So in TFT worlds, this is saying if I have an anomalous semisimple TQFT without point operators, so which is fusion in this sense, there's no sort of point insertion, then I also don't have codimension-1 boundaries to the vacuum. Every codimension-1 operator has a boundary to the vacuum. So everything can be recovered from the vacuum. There are no interesting codimension-1 operators. And every codimension-1 operator can be recovered from codimension greater or equal to 2 operators. And that's essentially the reason why in these Chern-Simons theories, why in these modular categories, you only need to consider lines and points, and you don't need to consider surface operators, because all the surface operators can be recovered from the line operators and the point operators. And the mathematical consequence is that if I have an invertible fusion n category, it has to be of the form modules of a braided fusion n-1 category. So there are no invertible fusion 2 categories, for example, which aren't of the form modules of a braided fusion 1 category. That's why if you care about invertible fusion 2 categories, you can just care about braided fusion 1 categories, non-degenerate ones. And if I have an invertible fusion 1 category, it's just equivalent to vect. This is something you can prove classically, you can prove sort of normally. It's not sort of too crazy, but the proof is a bit involved. And I think sort of using this machinery is actually much quicker to do if you've developed this machinery. And another comment for those of you who've been to Dimitri's talk last week, if not, you can completely ignore this. Things like the Drinfeld center of the categories of modules of a braided fusion category controls things that are called minimal non-degenerate extensions of braided fusion categories. And this is a modular fusion 2 category. This is a non-degenerate braided fusion 2 category. It's a Drinfeld center. It's a double. And so it has a non-degenerate S-matrix. And the fact that this is a non-degenerate S-matrix tells you a lot about the objects in this category. It gives you much, much better control about this category than you would have if you would sort of classically study it. And sort of this particular example, sort of the S-matrix for this category, we've studied in this paper and sort of used it there. Okay. So now let me finish with a bit of an outlook where this is leading. This invertibility of this S-matrix, you can think of this, it feels a bit like a sort of Poincare duality. We get sort of these homotopy groups, and we have sort of this perfect pairing between homotopy groups sort of in this diagonal way. So if you think of a fusion n category as sort of being analogous to a topological space, this was the point I was sort of trying to make earlier, then maybe you should think of a Reutter invertible fusion n category as somehow being analogous to a manifold, or maybe really to a Poincare space. It's somehow a property rather than structure on a space. And indeed, sort of using this analogy, what we are sort of currently doing, or what we're sort of, that's certainly sort of music for the future, and I can't say very much about this, but we're sort of, what we're currently sort of aiming for is to use this non-degeneracy of the S-matrix as a step towards a classification of these invertible higher fusion categories using something which is analogous to surgery theory. So what we're trying is there is a way to sort of try to kill high-level pi case. That's this completely different story. It goes under the name of ungauging. But then Poincare duality tells us that we've also killed these low-level pi n-ks, which are a priori much harder to kill, this S-matrix invertibility. And so by just sort of killing these higher homotopy groups, which are easy to kill, you've also killed these low-dimensional groups. And in the end, depending on which dimension you are, you get a possible obstruction in the middle dimension. But this is all work in progress. So thanks for your attention. And